In the previous lecture, we learned the direct comparison test, where the conditions to use the test is that the terms of the series are positive, and the conclusions are quite intuitive. So if we have a known series, and we know that the series is convergent, and if the series that we want to test, all the terms are smaller than the series that we know, then, since the known series is convergent, and all the terms of the series that we want to test are smaller than the terms of the known series, then the series that we want to test will also be convergent. On the other hand, if the known series is divergent, furthermore, all the terms of the series that we want to test are greater than the terms of the known series, then the sum of the series that we want to test will then be greater than the series that we know. And since it is divergent, so the series that we want to test will also be divergent. In this lecture, we are going to look at a similar test, which is called the limit comparison test. It has the same conditions as the direct comparison. So we want all the terms an and bn are positive. And if we can find a second series bn such that the limit of the ratio an over bn as n approaches to infinity equals to a finite value where c is greater than 0, then the two series have the same behavior. Why is that true? Because we are calculating the limit of the ratio. If the ratio equals to a finite value, that means the terms of the two series are proportional. So if one series converges to L, then the other series must also converge to the proportionality C times the value L. And when do we use this test? It is also similar to the direct comparison. So we use this test when the terms of the series is a quotient function with combinations of power n or exponential functions. Then we can choose our bn, the second series, as a known p series or as a known geometric series. Let's look at the first example. Let's test the series sum of 1 over 2 to the power of n minus 1 for convergence or divergence. For this series, we have an equals to 1 over 2 to the power of n minus 1. So let's let an be 1 over 2 to the power of n minus 1. An is a rational function, and we can notice that in the denominator we have 2 to the power of n. So that is the hint to compare with the geometric series. So I'm going to let my second series with terms bn, which equals to 1 over 2 to the power of n. Then let's compare the limit of the ratio. So the limit as n approaches to infinity of an divided by bn, which equals limit as n approaches to infinity of 1 over 2 to the power of n minus 1 over 1 over 2 to the power of n. Then let's factor out the highest degree. Limit as n approaches to infinity. I can rewrite the quotient as 2 to the power of n divided by 2 to the power of n minus 1. The highest degree is 2 to the power of n, so I factored this out. Then the denominator, I have 2 to the power of n times 1 minus 1 over 2 to the power of n. Then I can cancel out the terms that I just factored out, the 2 to the power of n. Furthermore, as n approaches to infinity, 1 over 2 to the power of n approaches to 0. So this limit equals to 1, which is greater than 0. In the series sum of bn, it is a known geometric series. I can rewrite that as 1 over 2 to the power of n. So this is a geometric series with r equals to 1 over 2. So this is a convergent geometric series. Sum of bn converges. So, by the limit comparison test, since the limit of the ratio is a finite number and is greater than 0, So the series for n starting from 1 of 1 over 2 to the power of n minus 1 also converges. Now let's look at the second example. Here we want to test the series sum of n plus 4 to the power of n divided by n plus 6 to the power of n. Similarly as before, we are going to factor out the highest degree and let the factor be the bn. So for this series, my an is n plus 4 to the power of n divided by n plus 6 to the power of n. You can notice that the 4 to the power of n and 6 to the power of n is the highest degree as n approaches to infinity. If you remember from the rate of growth, you know that an exponential function grows faster than a power function. So this too will be the highest degree. So let's factor this out. For the numerator, I'm going to factor out 4 to the power of n, then times n divided by 4 to the power of n plus 1. In the denominator, I'm going to factor out 6 to the power of n, then times n divided by 6 to the power of n plus 1, which equals, the terms that I factor out is 2 divided by 3 to the power of n. Then the rest remains the same. So I'm going to let this term be my bn. So if I take the limit as n approaches to infinity of the ratio an divided by bn, then this term will be cancelled out because I take this divided by this. So this limit also equals to the limit as n approaches to infinity of n divided by 4 to the power of n plus 1 divided by n divided by 6 to the power of n plus 1. And as n approaches to infinity, this two term approaches to 0. So this limit equals to 1, which is a finite value greater than 0. And I know that the sum of bn is a geometric series with r equals to 2 over 3, which is smaller than 1. So the series of bn converges. Then, since the limit of the ratio is a finite value that is greater than 0, so by the limit comparison test, the series for an, which is the sum for n starting from 1 of n plus 4 to the power of n divided by n plus 6 to the power of n, also converges. Let's look at one last example. Similarly, we are going to test the series for convergence or divergence. Here the series have terms an, which equals to the square root of n to the power of 4 plus 1 divided by n to the power of 3 plus n squared. So the technique to solve this is similar. The highest degree in the numerator is the n squared. So I factor out an n squared, and I'm left with 1 plus 1 over n to the power of 4. In the denominator, the highest degree is the n cubed. So n cubed times 1 plus 1 over n. So I'm going to let the terms that I factor out be my bn, which is 1 over n. And the rest remains the same. So square root of 1 plus 1 over n to the power of 4 divided by 1 plus 1 over n. So this 1 over n is my Bn. Then let's take the limit as n approaches to infinity of the ratio an divided by Bn. Then the term I factor out, 1 over n, it will cancel with the an. So this equals limit as n approaches to infinity of the square root 1 plus 1 over n to the power of 4 divided by 1 plus 1 over n. As n approaches to infinity, this term approaches to 0. This term also approaches to 0. So this limit equals to 1, which is a finite number greater than 0. And I know the series for Bn, which is a p-series. And the exponent is 1. So sum of Bn is a p-series with p equals to 1, which means this is a divergent p-series. And since the limit of the ratio an divided by Bn equals to a finite number greater than 0, so the series of an and series for Bn have the same behavior, which means by the limit comparison test, the series sum for n starting from 1 of square root of n to the power of 4 plus 1 divided by n cubed plus n squared also diverges. And that is the end of the lecture. In the next lecture, let's look at the alternating test, which is a useful test when we have an alternating series.